so this next talk, we're going to move to a generalization of the Grassmannian, the complete flag variety. And in lecture 4, Frank's going to talk like way more about geometry and way more generalizations. But this, again, will be fairly combinatorial for the most part, but we'll start with a bit of the geometric motivation. Gotta click. There we go. Okay, so let's start with the flag variety. Okay, so before, again, we were studying this Grassmannian of k-planes in Cn. And this is just a shadow of a much, much richer structure where we can think about, instead of having our points be k-dimensional subspaces, our points can be these flags that we saw in the first lecture. So a complete flag is just a nested sequence of vector spaces. So we have a one-dimensional vector space. Oh, sorry, that should be an Fi. A one-dimensional vector space sitting in a two-dimensional vector space, sitting in a three-dimensional vector space, and so on, until you get to the n-dimensional one, which is the full space. And then the flag variety as a set is just this set of complete flags. So we can encode a complete flag as an invertible matrix. Sorry, I switched. So I saw Frank was using the E's for the standard flag, and then I switched notation poorly. So any of these E's should be F's and not to be confused with the standard flag. Okay, so, but we can encode complete flags as invertible matrices, where we're getting our ith dimensional subspace to be the span of the first I rows of this matrix. And then once we have it encoded in this way, well, there's some squishiness in how we could have encoded. We can make a lot of changes to our matrix and still have the same flag. In particular, we can take a copy of any row and add a scalar multiple of it to a later row, and we'll still have the same flag. So this is coming out of your linear algebra. Okay, so for instance, like this one here, I took a copy of this first row, and then I subtracted it from the second row. And so that like kind of knocked that one out of the way, and we get something like that. I could have just like scaled it, and that's fine. That's not going to change the span of the first two rows. So I can scale the second row and get a 1 there. So yeah, something you can maybe like try to work out on your own is to convince yourself that really we can think of the flag variety as this quotient of the general linear group by this sort of left action that we have by lower triangular matrices. Hopefully, if I've done my linear algebra right, these conventions are all lining up together how they should. But here's just an example. We could take this lower triangular matrix, and we can multiply on the left. So we can take this matrix here, which was our starting thing. We can multiply on the left, and we get to this thing, which was our intermediate step. So we're just playing with row operations on matrices. Okay. All right, so the lower triangular matrix in particular, you might convince yourself is like you can think about it as rows sweeping downwards. So you can always take a copy of a row and add it to a later row. And that's exactly what the lower triangular matrices are encoding. And using these, we can bring any invertible matrix into a very special form where we have some permutation in Sn, where we have 1s in positions I, Wi. We have 0s to the right and below these, and we just have these arbitrary things elsewhere. So this is, again, like what we were seeing in the first lecture, but now we have square matrices, square invertible matrices that are full rank, full invertible. Okay, so yeah, our first U try is going to be just a little bit of linear algebra for you. So I want you to try and take this matrix down here and bring it into this form, where you have sort of these pivots that Frank was talking about, and you have maybe some free positions, but to the right and below any of these pivots, you just have 0s. Okay. So remember, we can add a copy of any row or a scalar multiple of any row to a lower row. Those are the things we're allowed to do to keep the same flag. cloud source. So go ahead, someone tell me a first step to try to bring this to this nicer form. Anyone brave? Let's see. So subtract row 2 from row 1. So if we do that, we'll change row 1. And so we'll have a different starting thing there. So that was kind of sweeping up if I heard it right. But we can sweep down instead, and that's okay. To make sure that the span of the first I rows stays the same. So let's instead, try and take row 1 and then sweep down. And we can kind of see, like, we want this one to kind of stay. It's probably going to be one of our pivots. And anything to the right of it would need to be 0, but there's nothing to the right of it. And we might want to use this one to cancel the thing below it so that there's no zeros down there, or so there's no non-zero things down there. So we can take this thing and leave the first row as it is, and then take the second row, and we can just subtract a copy of the first row from the second. Maybe this is exactly what you said originally, and I misheard. If it is, I'm very, very sorry. Okay. But we get something like that. Watch my arithmetic carefully. Does that look okay? Okay, now we have this annoying -1. What could we do? Yeah, let's scale. So we get this 2, 0, 1, 1, 0, 0, 1, 1, 0. And now we're already in this nice form. We have our pivots. Oh, nope, not quite yet. Yeah, subtract a copy of row. Thank you, Elizabeth. So subtract a copy of row 2 from row 3. 1, 0, 0, 0. Oh no. It's this thing touching the board. Terrible idea. Yeah, that looks fine. Okay, so when we do this, we get these pivots here. And then this was a 0. It could have been anything, but it ended up being a 0. But it's in this right form, where we have a permutation. In particular, our permutation is 3, 1, 2. And then we've brought this to this particular form. Okay, here's slightly neater. Okay. All right. So the permutation that we get from doing these linear algebraic things is unique. And this is another maybe like it's best to just play with some row operations and convince yourself. But what this lets us do is it lets us group flags by their permutation. And we call the set of flags that all have the same permutation a Schubert cell. And because we can bring them into this very special form, what really ends up happening is we can plot out basically a permutation matrix corresponding to our particular permutation. So here we're putting 1s again in positions I, W, I. And then we're like putting these cells, and a nice way to see where the cells go is you can kind of strike out these rays from each of these 1s. And what you really get here is something called a Rotha diagram. Okay. And so those pink stars, they're just free to be whatever they want, and they'll give you some flag that's in the same Schubert cell. Okay. Now this, because we could put it in this nice form, what we actually get is a nice affine space, and its dimension is going to be the Coxeter length of the permutation. It's a fact that the number of those pink stars is the same as the number of inversions. If you're looking for another exercise, you could try to translate between inversions and these pink stars. Okay. All right, so we can take the closures of these Schubert cells to get things called Schubert varieties. So these are a generalization of the Schubert varieties that we saw this morning. And they give rise to Schubert classes in the cohomology ring of the complete flag variety. And these classes form a linear basis. So again, this is very, very similar to what was happening this morning. And really our goal is to understand the product of two Schubert classes and how it expands in this Schubert basis. The Littlewood-Richardson coefficients from this morning are a special case of these structure constants, but there's a lot more going on. So that was a really, really brief overview of the geometric situation, but again, Frank is going to be giving a lot more details this afternoon about some more general things. Okay, but if we would rather not work in the cohomology ring, similar to this morning where we replaced cohomology classes with Schur polynomials, we can do a similar sort of trick. There's an isomorphism due to Borel that takes this cohomology ring to a quotient of just a polynomial ring by this ideal generated by the non-constant elementary symmetric polynomials, these EAs that we saw this morning. And so a question is, well, what are good polynomial representatives for the images of these Schubert classes? And Lascaux and Schutz and Berger gave us an answer to this question. They defined these Schubert polynomials. So a lot of this lecture will focus on Schubert polynomials and their combinatorics. Okay, so what is a Schubert polynomial? I'm going to start, first of all, with just like a crash course on permutations and some ways to think about permutations, just because people have a lot of different conventions, and this might be helpful for some of you. So again, instead of partitions from this morning, we're now working with permutations. So we have special permutations, these SIs, that really just exchange I and I plus 1, and these are the simple reflections. And the symmetric group is generated by the simple reflections subject to some relations. So there's this commutation relation. So these SIs can scoot past each other if their indices are far enough apart. There's this braid relation. So SI plus 1, SI equals SI plus 1, SI plus 1. And then also, if you take one of these things and you square it, you get back the identity. Because you can imagine if you switch I and I plus 1 and then switch them back, you're right back where you started. Okay. And I also wanted to say very particularly how to multiply or how I multiply. It's a warning that there's different convention choices out there. But we can encode a permutation as a permutation matrix. Again, we have these IWIs. This can be a useful way to think about it. Just a note, I often draw dots for the ones and leave the other spots blank. So how do we multiply? In particular, let's just multiply like arbitrary permutations by SIs. So if we multiply by SI on the on the left, what we're doing is we're switching the numbers I and I plus 1 in the string when we're looking at W in one-line notation. And then if we multiply on the right, we're switching W of I and W of I plus 1 in the string. And if you prefer thinking in terms of permutation matrices, this left multiplication, it's weird because of the way I've chosen to encode things, but it's going to switch column I and I plus 1. Normally you think of left as being row ops, but here there's a little twist you have to do. And if you multiply on the right by SI, you're really switching row I and row I plus 1. So let's just see an example of all of this to help us internalize it, and it'll help us when we go to actually work examples. So here with W being 1, 4, 3, 2, and I just being 1, this left multiplication is switching the numbers 1 and 2 in the string. And I've highlighted them in pink. Here at the level of matrices, we're doing a column up. So we're switching columns 1 and 2. If we multiply on the right, we're switching adjacent positions. So we've swapped this 4 and this 1, swapping W of 1 and W of 2. And then at the level of permutation matrices, we're swapping rows 1 and 2. All right, so now we're ready to define Schubert polynomials. So Schubert polynomials are defined recursively. So we start with the longest permutation in the symmetric group. We say longest because it really has the biggest possible Coxeter length among all the permutations in Sn. But in one-line notation, it's just things are as out of order as possible. So we start with n, then we have n minus 1, n minus 2, all the way down to 1. And this Schubert polynomial, we just associate to it It's just a monomial. And it's a very particular monomial that we sometimes call the staircase monomial. It's just x1 raised to the n minus 1, x2 raised to the n minus 2, and so on, all the way down to xn to the 0. And then if w of I is bigger than w of I plus 1, this is called having a descent at position I, then what we can do is we can get the Schubert polynomial for WSI by applying something called a divided difference operator to the Schubert polynomial for W. So this divided difference operator, it does this funny thing to polynomials where we take a polynomial f and we take f and we subtract off a copy where we switch xi and xi plus 1 in the polynomial. And then we divide the whole thing by xi minus xi plus 1. And by some miracle, instead of getting a rational expression, we can actually divide through, cancel, and we get just a polynomial back. This miracle is maybe, again, an exercise where if you're feeling motivated, you can convince yourself. Okay, so for example, if we're looking at S3, this Schubert polynomial for the longest permutation is just x1 squared, x2. And then to get the Schubert polynomial for 3, 1, 2, this is happening by switching positions 2 and 3. And so we're switching positions 2 and 3, so we're going to apply the second divided difference operator. So what we're going to do is we're going to take a copy of our polynomial. We're going to subtract off the copy where we switch x2 and x3. So nothing's going on with this x1. But we're switching x2 and x3, so this x2 needs to become an x3. And then we're going to divide by x2 minus x3. Okay. So looking at this thing, like we can factor out an x1 squared from the numerator. So that's good. Get this x2 minus x3 divided by x2 minus x3. Okay. And then these cancel, and we're left with just x1 squared. So that means that the Schubert polynomial for 3, 1, 2 is x1 squared. Okay. Now, to help you internalize this procedure, I'm going to have you try one now. So here's just a reminder about what the divided difference operator is. But we've computed together 3, 1, 2. I want you to compute the Schubert polynomial for 1, 3, 2. So first of all, how do we get to 1, 3, 2 from 3, 1, 2? Yeah, we can swap the first two positions. Oh, so we have 1, 3, 2. So this is really multiplying by S1 on the right. Okay, so that means we need to apply partial 1. So we're going to take this x1 squared. We're going to subtract off what happens when we swap x1 and x2. We're going to divide by x1 minus x2. And then we get x1 plus x2. You can factor the numerator and then cancel out that x1 minus x2. Okay, so we could play this game, we could compute the whole thing. It's maybe a good exercise, but I'm gonna just give away the answer. So for all of S3, here's all of our Schubert polynomials. What you're seeing on the left, this is actually drawing out this poset, which is called the weak Bruja order. So we're seeing these covering relations going down, looking at ways to swap things, and each swap, the Coxeter length actually goes down by 1. So that's what these simple reflections are doing for us. And then on the right-hand side, we have all the corresponding Schubert polynomials for all of these permutations. Now, you'll notice that there's 2 different paths that we could have taken to get to the identity. We could have gone along the left side of this chain or the right side. And it's a fact that these divided difference operators satisfy the same braid and commutation relations as the simple reflections do. So what this does for us is it doesn't really matter which path we take down in this weak Bruja order. Our Schubert polynomials are well defined. Now there is like a slight quirk. Again, a good thing to convince yourself. But if we take this partial I and we apply it twice, we get 0. So no matter what we plug in, we get 0. Okay. So it's very similar, but there's this extra funny different relation than SI squares to identity. Okay, so Schubert polynomials, they have a lot of nice properties. One of them is that they're stable under the natural inclusion of symmetric groups. So all this funny thing is saying is if we have like 2, 1, 4, 3, it's basically the same as doing 2, 1, 4, 3 and tacking on a 5 at the end. So we could think of it as being basically the same as tacking on a 6 to the end of that. So we can really think about permutations in S infinity by doing this sort of, this chain of inclusions. And Schubert polynomials, they also expand positively in the monomial basis. So on the previous slide, we saw, like, we had mostly monomials. We had one that was a little more interesting, the one that you computed. It had positive coefficients there. And it's not just a fluke. They always have non-negative coefficients in the monomial basis. And so whenever we're confronted with some set of numbers that's non-negative, we want to know, like, what do they count? And there's a lot of nice combinatorial formulas for Schubert polynomials. Today we're going to focus on 2 in particular. Okay. So the first one that we'll look at are these things called pipe dreams. So pipe dreams are built in the following way. We take an n by n grid, and we tile it with the following 4 tiles. So we can have this crossing tile. We can have this bumping tile. This is just like sort of a special one that goes on the anti-diagonal, and then this one lives below the anti-diagonal. So it's always just blank below a certain point. So we want to make some tiling so that we get a network of pipes that are starting at the top and ending at the bottom. And we have this extra condition that pairwise any 2 pipes cross at most 1 time. Okay. So here we can take this thing and we can associate to it a permutation just by thinking about where do the pipes start and end. So we can label the pipes along this top row, 1 through n, and then we're just going to follow the pipes and see where they lead. So 1 pops out the left, 2, we follow it down. If we get to a crossing, we just go straight. Follow it out, 2 popped out over here. The 3, we follow it down, 3 pops out over here. The 4, we follow it around, 4 pops out over here. So the permutation associated to this pipe dream is 1, 4, 3, 2. And then ultimately, we want to get polynomials out of this thing. So we had, in analogy to semi-standard tableau, we had a way of taking a tableau and producing a monomial. This time, what we're looking for is where the crossings are. We're going to count how many crossings showed up in row I, and that's going to give us the exponent of xi. So for this one here, it has a crossing in row 1, row 2, and row 3. And so this corresponds to the monomial x1, x2, x3. Now, it's a fact that the crossings actually uniquely determine the pipe dream. So sometimes it's easier to just draw the crossings rather than all of the squiggles, but the squiggles are helpful to figure out which permutation the pipe dream goes with. Okay, so the theorem Fomin-Krylov, Bergeron-Billy is that we can write down the Schubert polynomial as a sum over pipe dreams that trace out the permutation W. So for example, with 2, 1, 4, 3, I've written out all the different pipe dreams that go with 2, 1, 4, 3 that trace it out. Remember, pairwise pipes can cross at most one time. So these are the only ones that satisfy that condition. And then we have our different weights, again, coming from which rows the crossings are appearing in. Okay. Now, I just gave you these pipe dreams, and maybe you want to start working examples, and maybe you want to know practically how do I write down a bunch of pipe dreams and start thinking about them. So there's a nice algorithmic way due to Bergeron and Billy. So we're going to start with something called the bottom pipe dream. And the recipe for the bottom pipe dream is we're going to draw its Rotha diagram. So this is this thing again where we draw the permutation matrix. And again, I tend to like dots a lot instead of ones, probably because I draw Rotha diagrams. And so from each of these dots, we're going to strike out these rays below and to the right. And the stuff that remains is the diagram boxes. Okay, so I'll kind of color them in so you can see them. So these are our boxes. And then the rule for getting the bottom pipe dream is we take these boxes and we turn them into crosses, and then we just left justify. So we can just put cross, 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 because there's 3 in the first row. We can put a crossing there, and then there's 3 in the third row, and no more. And then I'm not going to draw all the elbows because it'll start to look a little bit cluttered, but you could draw in the elbows and you could confirm that this indeed traces out 4, 2, 6, 1, 3, 5. Okay. So now that we have this bottom pipe dream, we can use it to get the rest doing these things called ladder moves. So what are ladder moves? We take these pluses, and if you have kind of 2 consecutive columns of pluses where you have like a solid rectangle of some length, k, and you have a plus down here, and then you have elbows above, an elbow to the right of this plus, you can take this plus, and it can just kind of like climb the ladder, and when it does, it pops out at the top. And then, well, it left this position, so it left behind these elbows. Does that move make sense? There's a really special case of a ladder move that's the easiest one. I'm going to draw a dot. Ooh, can you see those tiny, tiny dots? Okay. So I'm drawing dots instead of elbows because, again, the elbows tend to get a little cluttered. But we can take just this one plus, and if it is surrounded by, like, to its right, it's diagonal, and above it, if it's surrounded by elbows, we can just take that plus, and we can just move it up, and it leaves behind elbows in its path. Okay, so here I'm demonstrating how we can take this one particular pipe dream, this bottom pipe dream, and then we can apply a bunch of these ladder moves. And as we apply these ladder moves, we trace out all the different pipe dreams that we can have. So this is the theorem of Bergeron and Billy, that you can reach any pipe dream in this way. And also these ladder moves, they preserve the permutation. They're designed exactly so that the permutation doesn't change and that you stay with this condition of pairwise pipes cross at most ones. Okay, so now I'm going to, have you try one. And I think Elizabeth sent out, or maybe, okay, so slides are sending, because I know it's hard to track these definitions. I also tried to paste really tiny the things that you need to start building these. But remember, draw the Rotha diagram, shove those, turn the boxes into pluses, shove them left, and then don't try to draw a bunch of elbows. Just like try to move some pluses around in a grid. See what happens. Okay. Again, if you are having trouble getting started, please flag me down. Or if you just want to say hi mid introductory talk 3. Pipe dream so far. Okay, does anyone have a ladder move for me? It's kind of hard to verbally say a move. Ah, we're not ready for you yet. Okay. Oh. Okay. So we can, for instance, take this plus, and we can just do one of those simple little moves and move it up this way. That's one that we can do. Is there any other ladder move that we can do from this one? Yeah. Excellent. So this bottom plus down here can pop up to row 1. So it climbed that very short ladder. Okay. Over here, we're just kind of stuck. There's no more ladder moves that we can do. But this one, we can keep going along. So, oh, just one from here. So we can go plus, plus, dot, dot, plus. And then we could also move up this last one down here. Okay. And that's all of them. So once we've tried all the possible ladder moves that we can try, then we've really generated all the different pipe dreams for this permutation. We could write down their corresponding monomial weights and get the Schubert polynomial for 1, 4, 3, 2. Okay, so that's pipe dreams. There's another sort of formula that looks very, very similar, but it's, well, different. And I forgot, crucially, one condition, which is that they form a network of pipes so that pipes start at the bottom and they end at the right. And there's N pipes. So if you just tried to randomly place down those tiles, it's not as simple as pipe dreams. You could get yourself into trouble and just have a lot of weird diagrams. So we still want a nice network of pipes that's going to produce for us a permutation. So we need these extra conditions. Okay, but we're going to tile the n by n grid now with 6 different types of tiles to get these bumpless pipe dreams. Now, they're called bumpless because this bumping tile is not allowed to show up. This thing that we're used to from pipe dreams, well, there's no bumps. Okay. Now, in a very similar way, we can write down a permutation. So we can write down this permutation just by going, this time labeling along the bottom, and then we can trace this 1 goes out here. This 2 pops out here, 3 pops out here, and 4 pops out up here. And so this also traces out 1, 4, 3, 2. And then we get a weight associated to our bumpless pipe dream in a different way this time. So instead of the crossings being important, now what's important is the blank tiles. So the weight is going to be xi raised to the number of blank tiles in row I. So here we have 2 blank tiles in row 1 and 1 blank tile in row 3, which is why we're getting this x1 squared x3. Okay. So the theorem of Lamley-Chamizono is that the Schubert polynomial is also a sum over bumpless pipe dreams. Here, again, I've drawn out 2, 1, 4, 3, and I've drawn all of its bumpless pipe dreams and their associated monomial weights. Now, this one over here, it should be looking super, super familiar because it's basically a Rotha diagram. We've drawn the permutation for 2, 1, 4, 3. We've drawn out these hooks, and now instead of having really sharp right angles, I've just drawn a little bend, but it's the same thing. So this one is called the Rotha bumpless pipe dream. And it's really the unique bumpless pipe dream for W that has no upward elbow tile. Okay, so this one is very handy if we want to generate all of the bumpless pipe dreams. So how do we write them out? We start from the Rotha bumpless pipe dream, and we do these things called droop moves. Now, I'm being a little bit vague here, but the idea is that within a rectangle, we have a hook. And this hook, it might have there might be other pipes in the region, that's okay, but there's a blank tile down at this bottom corner of the square. So there could be horizontal pipes or vertical pipes, but we don't want any extra elbows in this region. So if we're in that situation, we can then take this and we can map it to a new local little piece of our bumpless pipe dream where we have literally taken this pipe and we bent it and drooped it down into the blank tile, and then we get something like that. Now these are better to internalize just by doing it and trying it and maybe drooping wrong and then having someone tell you drooped wrong. But this is the idea. Here in the sense of oh no, you drooped wrong. So I drew first an allowable droop. We could take this pipe here, and we can droop it down into this blank tile here. And so that's what I've done in this first picture. Okay, so do we see the drooping? Okay, but over here, what's not allowed is maybe I take this pipe up here, and I try to droop it into that same rectangle. Well, I said there can't be any other upward or downward elbows in the region than this one turn for our pipe that's in play. And so here, I can droop this down, but now we have a bunch of pipes crossing a bunch of times, and we no longer have this pairwise pipes cross at most once. So this is just not allowed, no good, don't droop past these elbows. Okay, So, yeah. The theorem of, I guess, Lamley-Chamizono and kind of Lascaux is that you can start from the Roth bumpless pipe dream, and you can apply droops, and you get all the other bumpless pipe dreams for a permutation. Droops don't change the permutation. They're just a move that we can do to produce more bumpless pipe dreams for the same permutation. So here's an example again. If we have this bumpless pipe dream for 4, 2, 6, 1, 3, 5, we can start from the Rotha one. Here, for instance, I've drooped, to get to here, I've drooped this. And you can't really see the cursor when I, okay. But we can take this pipe here, for instance, and we can droop it into this box here. Okay. We could take this pipe here, we could droop it into here. Okay, so these give us a lot of little moves that we can do to help us write down bumpless pipe dreams. And so to that end, I task you with finding the bumpless pipe dreams for 1, 4, 3, 2. One. This Roth pipe dream, like a bunch of the pipes just don't have any blank tiles below them, so they're just frozen and stuck and they can't move. But this one pipe up here, it has a lot of different stuff that it can do. It has 3 blank tiles below it, and it can droop into any of these blank tiles. So just sketching this out. So this bottom portion was always just fixed. And sorry, I don't have as many colors in Adobe, easily accessible. So this is a little overloaded on the blue. But here, we could, for instance, droop this to here. We could have drooped it over to here. We could have drooped it down to here. And then, are we done? No, there's one more droop that can be done. So we can take this thing here, and we can droop it into the blank tile that's still below it. If you want to be like less rigid about what a droop is, there's more little sort of moves that you can do. But this gets the job done. Okay. So we see that there's kind of like different structures. If we're following like ladder moves for 1, 4, 3, 2 versus these bumpless pipe dream droops, they just give us sort of different ways of getting from one object to another. Okay. And in particular, just before we close out like this section of the talk, there's 2 different formulas for Schubert polynomials. At the level of like Schubert polynomials, you can kind of line up these pictures one by another in some sort of way so that you get a bijection that explains why these are the same formulas. So this is due to Yibo Gao and Daoji Huang. But if you want a little bit more structure, which I think might lead into some equivariant cohomology that we're going to see later, you can also talk about these things called double Schubert polynomials, which just carry around more information. So instead of just x's, there's x's and y's floating around. And what the y's are telling you is they're telling you the columns of the interesting stuff. So for instance here, like we have a crossing in row 1 and column 1, so we get an x1 minus y1. We have a crossing in row 3 and column 1, which gives us this x1 minus y1. So this is more information because if you just set all the y's equal to 0, then you're back to the single Schubert polynomial. And if you are trying to compare these two formulas and think about double Schubert polynomials, there's no way to just line up pipe dreams with bumpless pipe dreams that explains why these weights are also the same. There's no weight-preserving bijection if you insist on carrying around the y's, which we can see from this example. Okay, so these are two genuinely different formulas for Schubert polynomials with genuinely different properties. Okay, so I'm going to skip this you try, but you should feel free to try at some point. But use these formulas to explain the stability property of Schubert polynomials. Why is it that when you just append n plus 1 to the end of the permutation, you get the same polynomial, even though now we're in an n plus 1 by n plus 1 grid instead of an n by n grid? Okay, so now we have Schubert polynomials. Ultimately, we wanted to use them to understand this cohomology ring. The Schubert polynomials, when we think about them again as indexed by S infinity, we get a basis for this sort of extension of polynomial rings where we have now as many variables as we could possibly want. So if we take two Schubert polynomials and we multiply them together, we can expand over this Schubert basis and we get a bunch of structure constants again. And these are the same structure constants that were appearing from the cohomology ring of the complete flag variety. And furthermore, just like the Grassmannian, they're counting points in certain triple intersections of things. And so the fact that they're counting something means that they're non-negative. But what we really want is we want combinatorial explanations for this non-negativity. What do they count? We had these Littlewood-Richardson tableau before. What's the analog here? Okay, so we don't know in general, but we can say some things. So I'm going to tell you about a particular rule, but first I want to tell you just a little bit about the strong Bruhat order. So the strong Bruhat order is this transitive closure of covering relations given by multiplying W by these transpositions where Tij exchanges I and J. So again, we can talk about multiplication, multiplying on the left, multiplying on the right, positions versus outputs. But the idea is that we have a covering relation. If when we do a multiplication of this form, a swap of this form, the length of the permutation goes up by 1. And so here I've drawn this picture that shows all these covering relations drawn out. So it's very similar to the weak order, but now there's more covers. All right, so we have a way of multiplying arbitrary Schubert polynomials by a very special Schubert polynomial, and this thing is called Monk's rule. So we can multiply the Schubert polynomial for W by the Schubert polynomial for a simple reflection by taking the sum over these Bruhat order covers. So we're looking at specific covers where we have Tij, so that I is less than J, and I is less than or equal to K, and K is strictly less than J. Okay, so indices are never like our friend. Well, maybe they're some people's friends, but I do much better with pictures. So let's look at a picture to see how we can think about this. So I'm going to draw our permutation matrix. So we have 2, 3, 1, 4. And then I'm going to draw just like an extra bar after row 3 to remind me I want to swap dots across this bar. And multiplying by Tij on the right means I'm going to exchange row I and row J of this matrix. So I'm looking for ways to do swaps so that the Coxeter length goes up by exactly 1, and we swap dots across this bar. So for instance, I can swap rows 2 and 4. I can swap rows 3 and 4. So my swap has to go across the line. You might be tempted to try and swap 1 and 4, but you shouldn't do that. Visually, why you shouldn't do that is if you swap, there's like a dot in the middle, and that's going to make the Coxeter length just go up too much. So we don't want to do that. So we want to do these little swaps where there's no dots in between. Okay, so this is what we get. So this multiplication, we get the sum of 2 Schubert polynomials corresponding to these matrices that we found. I have off here in a bubble, it's an exercise. You could, for instance, use pipe dreams or bumpless pipe dreams to show that the Schubert polynomial corresponding to a simple reflection is just the sum of the variables x1 through xk. Okay. Here's another you try. Trying to decide if I have you try or if we maybe save this for exercises as well. I think we'll maybe save this for exercises. Okay. Oh, well, there it is. So if you don't want to be spoiled, just don't look at that slide. But yeah, okay. And then I have a few more exercises for you, again, for the problem session. But a permutation is Grassmannian if it has at most one descent. That's a position where W of I is greater than W of I plus 1. So I want you to try and think about why Grassmannian Schubert polynomials are actually Schur polynomials. So this Grassmannian and Schur, this should be like ringing alarm bells from this morning. And in particular, in the exercises, I'm going to have you try to think about this combinatorially. And then another thing that you can do, which might not be on the exercise sheet, but it might be worth thinking about, if a permutation is Grassmannian with descent at position k, explain how Monk's rule for multiplying by the Schubert polynomial for sk is actually just a special case of the Pieri rule that we saw from before. So these exercises are all about translating back and forth combinatorially between permutations and partitions, because all of the partition combinatorics is just like a subset of this permutation world. Okay. Now, there's another type of multiplication that we can do, which is no longer positive, but it's nice. So transition tells us how to multiply by a single variable. And really, we're getting this just straight out of Monk's rule by doing some appropriate cancellations. So we're multiplying by the Schubert polynomial for sk minus the Schubert polynomial for sk minus 1. That's really what xk is. And so we get sort of covers of this form where we have j that's greater than k, and we're getting these Schubert polynomials. And then we have a bunch of covers where I is less than k, and we're going to subtract those off. And some of our other Bruja orders just like canceled out. Bruja covers just canceled out in the wash. So some special cases of these transition equations are especially nice, and they have combinatorial explanations in terms of pipe dreams and bumpless pipe dreams. So the first one is cotransition, which I'm not going to write out for you in indices, but I'm just going to show you a picture. So what we can do is if we have a permutation where we can take kind of, draw its Rotha diagram. So 2, 1, 4, 3. And then look at these diagram boxes. There's always going to be some subset of diagram boxes that are kind of top left justified. So if you find yourself, if you're able to add a box to one of these corners and get a partition, then you can start playing this game with pipe dreams where you take the pipe dreams for your permutation and you just kind of plop down a new crossing. You replace an elbow with a crossing in that position in every pipe dream. And what's happening here is this cotransition combinatorially is saying, well, we're going to group things together in the right way. When we do this potentially rough procedure, it's actually nice, and we get permutations. We see pipe dreams for the correct permutations that we're seeing from the transition equations. So they get grouped together in this nice way. So cotransition is nice in terms of pipe dreams. And then there's also like Lascaux and Schützenberger's transition equations, where we're thinking about these maximal transitions. And the idea is you look for your permutation and you look for the position of the last descent. So that's row 3 here. And then at the level of bumpless pipe dreams, I'm going to be a little bit vague, but you can ask me more about it. But what we're going to do is we're going to, in this Rotha pipe dream, try to swap pipes so that we cancel the last diagram box in the last row of the Rotha diagram that has boxes. And so we can take these 2 pink pipes and we can swap them and we get this new permutation here. And well, the consequence of swapping those 2 pipes was we knocked that diagram box away. And that diagram box should have been contributing weight. It should have been contributing an x3. So we write this x3. So we're really doing transition to this permutation. And then we've rewritten the equation so that we don't have a minus sign, so that we just moved those terms all over to one side. But we end up here also doing these swaps. But now when we do these swaps, we just like treat it like a new pipe dream. So things go like this. And the new bumpless pipe dreams that we get are corresponding to the different permutations that we'd expect to see from these transition equations. So the point is that pipe dreams and bumpless pipe dreams are each showing us different structure of the combinatorics of Schubert polynomials. So they're both useful ways from different perspectives to think about these things. So again, unlike Schur polynomials, we don't have nice combinatorics, which computes these arbitrary structure constants. Some special cases are known. I'm imagining you can expect to hear a whole bunch more during the course of this workshop. So I'll go ahead and stop there.